today. I want to go over the stream data flow pulse way it goes through the calculator. I suppose we're going to follow that. So the controller um, has a little each button's actually kind of a 5-bit encoder. It sends out 4-bit serial data, but I still gotta have a little start pulse. So every button has the fifth torch that tells it to send a signal. And so we're sending a 4-bit signal into the calculator. That signal tees off and it goes to two different receivers, so to speak. And one's down here on a lower decoder that handles all the functions. The other one's up top on this bigger decoder that writes all the digits and the little C to the displays up here. And when we write them, this guy only cares about numbers, and this guy only cares about functions. He only sends out pulses on different lines to tell different shift registers to move or whatnot, and he just converts 4-bit digits into 7-bit serial data. That serial data is pumped into all four displays, and only the one that's open can receive it. And only the one that's open also has the cursor blinking. So, um, after we pump it to all four and one of them catches it, that 7-bit serial signal goes to each one of the segments of the 7-segment display. That's how we're printing our different digits and letters and such. And of course, the other end of that signal goes down to the functions block, but more than that, it goes across the top into a little repeater RAM which locks in the digits corresponding with whichever. Sorry, hold on. Uh, so, each one of these repeater RAMs has an according cell up top, and it also goes into what appears to be a ripple carry adder, this blue and lime, but that's not actually a ripple carry adder, that's reverse double dabble or half and dabble algorithm, converting human numbers, as it were, into computer numbers so we can do math with them. Orange here is my main adder and subtractor. The B input goes through my little inverters here, so when I want to go to subtract mode, I turn on my inverters and my carry. I can't do negative numbers. It will just print an E. This set of pistons is the digit counter where it counts binary counter all the way up to 255. It's a bunch of one-tick generators in a row. This is the reset line, which just catches the blocks and sucks them back up, resets it to 0. There's little comparator locks in line with these outputs, and they're also in line with another set of outputs up here. Um, these outputs come from the multiplier, and these come from the adder subtractor. There's a torch in between the two that toggles, as it were, and just switches polarity between the two lines. So either one side or other side can talk to this ugly diamond monstrosity, which looks like a horrible cowlick hanging off the side of my calculator, but it's double dabble. The headache of converting computer numbers back into human numbers. We can do all the math in these little parts down here, but just to switch the number, it's got to be this huge thing. It can be a much smaller machine, but I can't really understand how they work, so I can't debug them. This is just a bunch of decoders switching anything larger than a 4, adding 3 to it, and they're staggered, simulating the shift all the way down. I just built it. I knew the algorithm. I built it large enough for 16 bits, and then since I only can go 99 times 99, I trimmed off everything I didn't need, essentially down to 14-bit. Um, the multiplication is handled back here in this pink and orange registers. And like I said, it's not completed. It just writes to this register. Um, I'm working on that currently, and I'm going to solve it very soon. Once everything finally gets through the double dabble, it goes down to the bottom here, which is a bunch of gates per cell, if you will, and each 1 line, 2 line, 4 line, and 8 line is merged, but only one of them can talk at a time. And those outputs go into the sandstone decoder up here. And I don't know if this looks familiar, but this is the same thing I have on top. It's a digit writer. This one writes the digits for the answer. It converts the 4-bit back into 7-bit for our 7-bit serial displays. The same shift register that unlocks the different lines in the double dabble also simultaneously unlocks the bottom answer displays, and that's how we shift our answer in there. Oh, so that's basically the flow of a mathematical equation through the calculator. Um, my display driver printers, one down here and one up here, and my functions operations are all coming out of these output lines down here, purple brick, sandstone, and such. This is like equals, and it lets the signal through, goes to wherever it needs to go. When we change modes, it just changes this purple shift register, goes to the display driver for my equations display up here, and it's raining again. Oh my gosh, hang on. Where was I? The on and off little guy's hidden way back up in here. I actually went with a mechanical system, dropper T flip flop on that. Um, I like using those in certain places because you can just charge just the bottom. Like on this one down here, when I want to reset it and make sure it's always going to reset to the correct side, I can just reset on the bottom block. And it doesn't toggle, it only goes, up. My reset signal is these stone brick slabs, and it goes along to all 4 resettable shift registers. The sandstone shift register does the upper displays. This polished dorite shift register does the answer displays. Um, and these shift registers are also merged. That one's merged with the double dabble. This one is merged with the RAM right lock system. The other shift register is for the mode, which is the purple one down here. There are some other flow steps that I'm forgetting, but this video is starting to get long again. It's pretty much a basic overview of the flow through of current and operation of the calculator, and I'll get more in depth with the individual components and such in the next few videos. Alright guys, cool, thanks, and I'll see you soon.